multi-degree of freedom systems. Sometimes a system can have multiple degrees of freedom due to multiple masses or nodes that are connected together by springs and or dampers, and these degrees of freedom are able to move independently of each other, which means that we could hold one still and move another degree of freedom. So for example, if we have two masses connected by a spring, we could hold one mass still and move the other mass because the spring is able to get longer and shorter. And we can also hold the other mass still and move the first mass left and right or further and closer because the spring is stretchable. So this is a case where we can have multiple degrees of freedom in our system. Now, we can also have what are called nodes in our system. These are going to be locations where multiple springs or dampers are going to be connected. A node is going to be treated as just a massless and inertia-less connection point, whereas a mass, as the name implies, can have mass, and if it's rotating, could have inertia. So what are the steps we want to take in multi-degree of freedom systems? Well, pretty similar to what we did for single degree of freedom systems. What we need to do is for each degree of freedom we have, we're going to create a free body diagram, and from that free body diagram, be able to get an equation of motion. So each node, each mass gets its own free body diagram. Usually we'll get one equation of motion per free body diagram because each free body diagram will have only one degree of freedom of that mass or of that node. But in more complicated systems, we could have multiple equations of motion out of a single free body diagram if it could translate and rotate, say, or it could translate in two directions. Now, as one warning, and this will come up when we have prescribed displacement or an input displacement into our system rather than an input force. In this case, usually it's going to happen on a node. We do not want to model that node. We don't want a free body diagram of it because we know that node's displacement, but we don't know the force that's acting on it that's actually causing that displacement. So that's the one exception of when you should be drawing a free body diagram for a degree of freedom, if that degree of freedom is the input into the system. Okay, at this point we have our equations of motion. They are in the frequency domain. We've taken the Laplace transform. We are interested in getting one or maybe a couple of transfer functions out of this. Once we have all of our equations of motion, we want to identify the inputs and the outputs in the system. So the outputs are going to be the things we don't already know beforehand. So usually it would be like the positions of masses in the system, sticking with a mechanical system now, or it could be positions of nodes except for nodes that have the prescribed input displacement. Then we want to count up the number of inputs we have. Typically, we're going to have in this course for a mechanical system one force input or one displacement input, but again, in more complicated systems, you could have multiple inputs. You could have multiple forces acting on masses. You could have two locations where you are prescribing the displacement. So count up the outputs and the inputs. And what we need to make sure we have is the same number of equations of motion, or really equations, as we have outputs. That will tell us that we are able to get the transfer functions that we're interested in. Now, not all of the equations necessarily are going to come from equations of motion. There might be other things external to just the forces acting on the system that give us equations. So we could have gears that are meshed together, and we know what the relationship is between the radii of the gears and their angular displacements or their angular velocities. When we start talking about electromechanical systems, we're going to have some additional equations that are going to relate the electrical side to the mechanical side. So certainly we'll have equations of motion, but maybe some other equations as well. Count those up. Do they equal the number of outputs that we have? Then we want to solve for our desired transfer function using algebraic substitution. Even with only 2 degrees of freedom and then usually 2 equations of motion, this substitution can sometimes start to get difficult, and that only increases the more outputs that we have, the more degrees of freedom that we have. So I'm going to typically be using Mathematica to assist in these more complicated systems. However, we can by hand do algebraic substitutions to get the desired transfer function. What we need to check is to make sure that when we think we have our transfer function, that the right-hand side has no dependent variables. The right-hand side should have constant terms and s terms. S is the independent variable when we're in the frequency domain, and that's it. And for the problems we're going to be looking at, we are going to have a polynomial expression of s in the numerator typically, and a polynomial expression of s in the denominator. If there is another dependent variable on the right, then something went wrong with finding the transfer function. You possibly did not generate enough equations, or you did not do the substitution correctly. So only s's and constants in transfer functions. And when we write them in the standard form, you are going to write it in descending powers of s. So you'll have one coefficient in front of, let's say, an s cubed term, plus another coefficient in front of an s squared, plus another in front of s, plus a constant in the numerator and the denominator. It depends on the degree of the polynomial, but you have one coefficient in front of each descending power of s. And this is going to be done to make it much easier to then simulate our results in MATLAB. As in MATLAB and in other systems that have or support transfer functions, they are expecting you to put in the coefficients of your transfer function in descending powers of s. So we will see that in the first two examples we look at using transfer functions and then simulating their results in MATLAB.